Hello, everyone. As it turns out, I didn't record my lecture on Thursday, and so as a result, I have uploaded a repeat video. So I'm recording that now. Now, as you can hear, there's a fan in the background. Yeah, uh, it is what it is. I hope that you can hear me well. Now, one thing I wanted to mention is that actually, I already mentioned this during class. So, okay, so last class, or actually a couple classes ago, we started talking about filters. We started by defining what a filter was. So remember that when we look at our frequency response, h of j omega, its magnitude, if it looked like this, we called it a low pass filter because for low frequencies, you had that the frequency response was not zero. And for high frequencies, you had that the frequency response approached zero. We also defined what a bandpass was in the previous lecture, which looks something like this. And then we also defined what we call a high pass filter, which looks something like this. Now, typically, if you have for a low pass filter, by definition, there cannot be any zeros at zero. So this is like s squared plus 3 plus blah, 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 blah. There cannot be any zeros at zero. You can have zeros. So you could have like, but that zero cannot be at zero. And also you need more poles than zeros. The reason for that is because ultimately you need to end up with a negative slope so that the response will go to zero as frequency goes to infinity. Now, for a bandpass, you need to have at least one zero at zero, and then you need to have more poles than zero. So basically here you need no zeros at zero and more poles. So if you don't have any zeros at zero and you have more poles than zeros, that's a low pass. If you have one or more zeros at zeros, but you have more poles, that's a band pass. And then here, if you need to have at least a zero at zero, and then s plus blah, blah, blah. And then you have less poles than zero. That's called a high pass filter. So what do I mean by that? If I gave you something that looked like s squared plus 3 s cubed plus 3 plus 5, or plus 3s plus 5, let's say. For this particular filter, we have more poles because the polynomial is higher. So that means it could only be one of these two. Then if we look at the numerator, there's no zeros at zero. So that means that this is a low pass filter. Now, if I change this and I basically made it look like this, that's a band pass filter. I could have also done this. That's still a band pass filter. Now, if I make this cubed, or sorry, squared, this is a high pass filter, less than less poles than zeros, less than, or equal, sorry, less poles or equal. So once I made this squared, now it became a high pass filter because the number of poles equals the number of zeros, and you have at least one zero at zero. So that's another way you can identify filters from just looking at the Laplace transform of the transfer function. Okay, so that's just review of our previous lecture. Today we're going to talk about how to design high pass filters. Before we do, let's go over some. Okay, so it's asking us, is this a low pass, band pass, or a high pass filter? So I could either derive the transfer function for this. So let me just derive that. So we're going to have that I out over V in is actually equal to 1 over the impedance. So 1 over R plus SL plus 1 over SC. And remember that we don't like these S's in the denominator, so I'm just going to multiply by S and divide by L. So I'm going to get S over L divided by S squared plus R over LS plus 1 over LC. So I wrote this term first, that's why we have S squared. And I just multiplied the top and bottom by S over L, S over L. And that's how I got the S over L in the numerator and the S over L in the denominator. Sorry, the S squared plus R over LS plus LC. So based on our previous discussion, we have we have 1, 0 at 0, and more poles than zeros. So basically we have 2 poles. That tells us that this is a band pass. Okay, another way we could have done this is the method that I gave you on the, okay, so another method we could have done this is by looking at h of j0, which in this case it would be j0 over L, j0 squared plus R over L, j0 plus 1 over LC, which is just 0. And then we could have looked at the limit as omega goes to infinity of h of j omega, which is going to make some mathematicians math, but we're going to get basically j infinity over L. And then in the numerator, we have j infinity square plus R over L, j infinity, plus 1 over LC. Now remember, for these cases, you would have to use L'Hopital's rule. And because you have an infinity squared, this actually is 1 over infinity, which is equal to 0. Okay, so you could have gone through the math. I mean, this is a terrible way to arithmetically take limits. But if you were to use L'Hopital rules, it all amounts to you have a higher power in the denominator. So each time you apply L'Hopital's rule, you're going to get one lower power. And eventually you're going to end up with 1 over infinity. Okay, so then we would have gotten that indeed h of j0 is 0, h of j infinity is 0, therefore it's a bandpass filter. Now there's a third way which I showed you in class, which is the shortcut way, which is you can just use the impedances that each of the elements has at 0 and infinite frequency. So remember that j omega L is equal to, so basically we have j omega L, and if omega is 0 and omega equals infinity, we're going to have that j omega L is 0, j omega L is infinity, and j omega 1 over j omega c is just going to be infinity and 0. And so when omega equals 0, we're going to have basically that this is V in, we have our resistor, our inductor at omega equals 0 behaves like a short. So this is your L, which has 0 impedance. And your capacitor behaves as an open because it's infinite impedance when omega equals 0. So if I look at the current coming in, well, there's going to be 0 current because this is an open circuit. Okay, now let's look at the circuit at omega equals infinity. Now we have V in, R. Then now our inductor behaves as an open and the capacitor behaves as a short. And again, I out will be 0 because there's no current flowing through an open circuit. And since I out is 0, in both cases we're going to get a 0 response independent of what V in is. And this is a band pass. So at this point you have 3 ways you can determine whether something is a low band and high pass filter. And guess what's going to happen in your final? You might be given a circuit and you're asked, is this a band pass or a circuit and the output? And you're going to be asked, is this a band pass, high pass, low pass? You might be given a transfer function and you might be asked, is this a band pass, high pass, low pass? Or you might be given a frequency response and you're asked, is this a band pass, high pass, low pass? In all of those cases, you should know how to approach this type of question. Okay, so that's kind of review. Let's go over one more example before we kind of drop this. Okay, so is this a low pass, high pass, or band pass filter? So this is the output. So our transfer function h of s is just v out of s divided by v ins of s. In this case, it's probably easiest just to do our little trick where we look at how the impedances behave at omega equals 0 and omega equals infinity. So let's look at that. At omega equals 0, we have V in. This behaves as an open, j omega L. No, j omega L behaves as a short. This behaves as an open. This behaves as a short. And then we have RL, V out. So in that case, V in equals V out. So H of J0 does not equal 0. That's what we care about. And now let's look at omega equals infinity. So we're going to have our circuit. Our inductors now behave as open and our capacitor as short. And then we have a resistor here, RL. And as you can see, this capacitor here, well, it's shorted. It's not connected to anything. So H of J infinity equals 0. So this is a low pass filter. This is actually your topology for a third order Butterworth that we used in the previous lecture. Okay, so those are 2 examples. You should get comfortable with these. They're going to show up in the final, whether you're in West Lafayette or Indianapolis. This is one of the things we want you to know about filters, identifying what kind of filter a circuit is. And so it's important. It's going to be in the final. Like it's guessing what's going to be on the exam is not very difficult. Just look at what's important. That's going to end up in the exam. Like it's not that. It's very simple. Okay, so just like in the low pass filter lecture, we have our high pass filter design, and we're going to have 4 parameters associated with them. H min, and then we have omega stop. Now for the low pass filter, for the high pass filter, we need that all the RL responses are smaller than H min for omega less than omega s, In the case of the low pass filter, it was for omega greater than omega s. So basically, we need that our response is smaller than this H min for all frequencies less than omega stop band. And then the second set of parameters is that we need our response to be greater than H max for all frequencies greater than omega passband. That's what we're going to call our low pass filter. And just as before, this is like the twilight zone, transition. Anything can happen here. This is the no filter land or whatever. Anything can happen. So that it's basically, we're doing the same thing. We have the same 4 parameters for a low pass as a high pass. The main difference is that now the stop band is at the low frequencies and the pass band is at the high frequencies. For a high pass filter, for a low pass filter, the stop band was at the high frequencies and the pass band was at the low frequencies. As you will see, we will actually use a weird strategy to solve for designing high pass filters. We're actually going to convert our high pass filter design specs into an equivalent low pass filter, and then we're going to convert that low pass filter into a high pass filter. And so to do that, first I have to teach you this conversion from low pass to high pass filter and vice versa. And so that's what we're going to go over in the next few slides. Okay, so just to reiterate, stop band, omega stop less than omega s. Pass band, omega greater than omega p. And then we need our response to be greater than H max, and we need a response to be less than H min. And that's it. And just like in our low pass filters, instead of working with gains, we're going to work with losses. So basically, remember that our loss is just 1 over H of S. So H max becomes A max. H min becomes A min. And so we need that our omega stop band has a bigger loss yeah, so this is actually the low pass filter slides, but just remember that we're working with losses basically. And with losses, it means that you're going to have a higher loss for the stop band and a lower gain for the pass band. Okay, let's keep going. All right. So this is actually the main thing that we're going to leverage in our lecture, which is low pass to high pass conversions. So as it turns out, if I have this H of j omega, which is my frequency scale Butterworth filter response, if I replace my argument, which is from omega, from H of j omega over omega c to H of omega c over omega, I get a high pass filter with a cutoff frequency still at omega c. So basically, if I plug in omega c here, I'm going to get 1. So I'm going to get 1 over the square root of 2, which is our -3 decibels. And if I plug in here omega c, I'm going to get 1 over the square root of 2, which is 3 decibels. Additionally, for this particular case, if omega is large, then this becomes 1 over infinity, which is effectively 0. So my response will tend to 1, or 0 decibels. Whereas in contrast, if I plug in 0 here, then this thing will be 0. And so this will be 1 over 1. And as the frequency tends to 0, my response will tend to 1 or 0 decibels. So this one has a high pass filter. This one is a low pass filter. Additionally, for infinite frequencies here, if I plug in infinity here, I have 1 over infinity, which gives me 0. And if I plug in 0 frequency here, well, that now I have 1 over infinity, which again gives me 0. And so for 0 frequency, I get 0 response. For infinite frequency here, I get 0 response. So what we just found out is that if I take an h of j omega and I replace it now with and I turn it to and I find a circuit that gives me a frequency response that's 1 over omega, that's going to give me a way to convert a low pass filter to a high pass filter and vice versa. Now, in the past, how did we go from h of s to h of 1 over s? Well, so if you remember in our previous lecture, I was saying that if I had a circuit and I was feeling patriotic that day, and I said that if I have a circuit that's like R, and then I have a 3S, and then let's say this is V out, and then let's say I wanted to go from h of s to h of 1 over s, all I had to do was take every s and replace it with 1 over s. So basically, to find a circuit that has that, I just would basically go here and replace my impedance with 1 over s times 3, and that's it. So what this means, of course, an inductor has a capacitor, has an impedance that's proportional to s. A capacitor has an impedance that's proportional to 1 over s. And so as it turns out, if I want to convert a low pass filter to a high pass filter, I just have to take every capacitor and inductor. I just have to take every capacitor, replace it with an inductor, and every inductor replace it with a capacitor, and now I have a high pass filter. That's all that means. And so what we're actually going to do to design high pass filters is we're going to take our high pass filter design parameters. We're going to come up with low pass equivalent parameters. We're going to design a low pass filter, and then we're going to convert that low pass filter into a high pass filter, and our final design will meet our specs. So that's what we're going to do. Okay, so let's look at this process a little more closely of what I was alluding to. So if I have this circuit here, and it's a low pass filter, so here's my circuit, and then I have the impedance is just 1 over SC. And for this circuit, you know, oh, this is just a mess. Okay. For this circuit, we have that the V out over Vn, this is just a voltage divider, is just 1 over SC times 1 over R plus 1 over SC, which is just simply 1 plus SRC, basically. Yeah. So I just multiplied it out. Now, I can take this capacitor and I can replace it with an inductor as L, where the L is just equal to 1 over the original capacitance. So as L nu is just C old. So I'm going to define this as C old, and then this will be my inductance L nu. So that the impedance is just going to be 1 S over 1 C old. Okay, what is the new transfer function? Well, the new transfer function is just V out over V in. This is still a voltage divider, so it's just going to be SL divided, or L is 1 over C, so I'm just going to write 1 over C. 1 over C. Oh, here, let me just redo this. Sorry, I apologize. S over C times R plus S over C. And then I'm just going to multiply out the C, so I'm just going to get S over S plus RC. And actually, I'm just going to go ahead and divide both the top and bottom by S, and so that I get here that this is actually equal to 1 divided by CR over S plus 1. So that you can clearly see that the only difference between this transfer function and this transfer function is that I replace the S with 1 over S. Now to get it into this form, all I did was divided this by S and divided this by S, so that then this became a 1. And then when I multiplied this by R, I got RC over S. And when I multiplied this by S over C, I just got 1. So these two things are equivalent, basically, as you can see. But you see what's interesting. By doing this transformation, I went from H of S to H of 1 over S. And by design, I also went from H of J omega to H of J over 1 omega. Okay, so now that we've gotten there, okay, there should be a negative sign here, but it turns out that all of our functions are real, so as a result, h of negative j omega in magnitude will be the same as h of j omega, so I'm just gonna say h of j omega. Okay, at this point, the book decided to do an additional thing, which is we need to frequency scale by omega c in order to get our final response. So we just simply use what we learned from our previous lecture to frequency scale this by 1 over omega c. Sorry, we frequency scale this by omega c, not by 1 over omega c. I apologize. And then that gives us our final circuit with this response here. So as you can see, we can convert a low-pass filter Butterworth that's normalized and convert it to a normalized high-pass Butterworth filter. And we're going to be leveraging this for our design. So before I actually show you the recipe we're going to use, what we're going to actually first do is we're going to take our design parameters for a low-pass filter. So this low-pass filter has a stop band that requires this minimum loss, and a pass band that requires this minimum gain. And we're going to replace it with equivalent low-pass parameters, so these capital omega p's. And here is our transformation. So we're going to define our capital omega as omega p over omega. So what that means is that omega p, the capital omega p, is equal to omega p over omega p, which is just going to be 1. And capital omega s will be equal to omega p over omega s. And our cutoff frequency will just be omega p over omega c. Sorry, omega p over omega c is our capital omega p. So all I did was the following transformation. But now, since I'm going from a dependence of omega to a dependence of 1 over omega, now our design parameters are defined in a way that now this looks like a low-pass filter Will you have a small loss for less than omega p, and you have a large loss for less than capital omega S? So we're going to design a low pass filter with these specifications, that the pass band is um, up to 1 and the stop band is greater than capital omega S. Okay, so that's what we're going to do. And then once we have our design, all we have to do is convert it to a low pass filter design. So we're going to use this formula to basically replace every capacitor and inductor with an inductance and capacitance respectively. So that's what we're going to do. Okay, so this is actually what you need to know, whether you believe anything that I said in the previous slides or not. You just need to know how to apply this. You know, there's this story about dream catchers, where Niels Bohr used to have one of these dream catchers outside of his home, and then people used to ask him about it. So you know the dream catchers. And then people were like, "Oh, so do you believe in these dream catchers that they work?" And then he used to always reply, "No, I don't believe they work, but I was told that they work whether you believe in them or not." So whether you believe that this works or not, whether I convince you or not, doesn't matter. It still works. So same thing like the dream catcher. You just need to know how to apply it, and it will work. You don't need to believe that it actually works. All right, so let's go through the process. So let's say you're asked to design a high pass filter with an omega stop band of omega S and an A max of sorry, and an A min of A min. So you need your filter to be out here, and then you have a pass band omega P. So to design a high pass Butterworth filter, the first thing you're going to do is you're going to find out what your new design constraints are for a low pass filter, or your capital omega S, which is just going to be omega P over omega S, and your capital omega P, which is just going to be omega P over omega P. And then you're just going to design a low pass filter. So here we have A max. This is the same A min and A max that you had from your previous. So same one. And now you're going to have a capital omega S, which actually, oh God, what am I? Erase. My pen decided not to work. It's too much in the corner, so it just falls out of the screen. Capital omega S, and then capital omega P. Now note that because my transformation takes omega and converts it to 1 over omega, a smaller omega comes out later and a bigger omega comes out before. And so, and now what we're going to have is basically that we need it to be something that looks like this. Oh God, I can't draw. Can't draw in my pen. It's just being annoying. There you go. Okay. So we're gonna have here, I'm gonna change the color just to be more precise. So for the pass band, we need to be very small loss, very small loss. Then we need to slowly increase slowly increase, and then increase up. So we're gonna design this filter. So here's kind of the design constraints. Now, in order to design this filter, we're gonna use the same process as before. So this low pass filter, we use this formula with omega s over capital omega p plugged in. Of course, omega p is 1, so you don't really need to plug it in. And then you find your minimum order. Once you get your minimum order, then we're just going to choose the appropriate circuits or base normalized circuits from our table of circuits. Then once we know the order we're going to use, then we just simply choose an omega cutoff that we need to scale by. We scale the circuit, and then we're going to get our low pass filter. And then what we're going to do is convert that low pass filter to a high pass filter using this formula here. And then that's it. That's going to be our design process. Now, one thing to note is that you could have used a conversion here where you used 1 over omega p as opposed to omega p, and actually conceptually it would have been much simpler. So basically you could replace all of these omega p's by 1s, and then just replace it here by 1s, and you would get the same result. The book decided to add this extra scaling, so that's why I teach it this way, although it doesn't make any sense to me. But I don't know why they decided to rescale it again. It doesn't make sense. It's kind of like these roads where you have like multiple exits. And imagine you're coming in through this road, and instead of going out this way, you first do a lap and then go out this way. That's what the book did. But so we're just gonna go with it. One semester I tried to remove that omega p, and it confused everyone because some people are reading the book, others are not. And so I just kind of decided, okay, we're keeping it, but it doesn't make sense to me. But if you follow this process, you won't be wrong. That's what I'm going to say. Either with the 1 or with the omega p's. Okay. Okay, so before we call it a day, I'm going to go over one example. I think this is fairly straightforward, to be honest. And you just need to know how to apply these heuristics. So if you don't understand, pause the video and actually try to solve this thing as I do. So the first step is, given these design parameters for a high pass filter, we're going to find what our omega p is and our capital omega s is. So capital omega p is going to be omega p over omega p, which is just going to be, in this case, 1400 divided by 1400. Well, it's always 1, but it's just 1. And then omega s is going to be omega p over omega s, which is just 1400 over 800, which is just going to give me, what is 1400 over 800? 7 over 4. Okay, so basically we have, if we look at our omega, we have 7 over 4, and then we have 1 here. And so if we look at our A min, or A max and A min, we need to have kind of a small, we need to be kind of under here, and we need to be above here for designing our low pass filter. So this is our low pass. We just choose a different color, so we need kind of a response that looks something like that. This is the loss. Okay. Okay, so now we found our omega p and our omega s. So now we just need to design a low pass filter with those specs. So we just need to design a low pass filter with those specs. So remember, we need to first find minimal order, and choose order. Then two, choose an omega C and frequency scale. So let's do that. Okay, so we have this. Note that this is actually 7 over 4. That's what that is, 1.75. Okay, so to find our minimum order, we're just going to go ahead and plug in a min, which is given to us. And remember, we're going to use the decibel devil because this is actually a decibel to linear conversion. So we're just going to plug in 3 for this. And then we're going to plug in for a max, it's 2. And then, so we're going to have basically 1 over 2 log base 10 of 10 to the 0.3 minus 1 over 10 to the 0.2 minus 1. And then we need to divide that whole thing by log base 10 of 1.75 divided by 1, 1.75 divided by 1, which is just 1.75. So let's say we plugged that into our calculator and then we get 0.5, or I don't know, 0.4 something. I think that's the right answer. Anyways, we're going to get some number. I think it's 0.4 something. So we get a number here. There you go. We got a number. So now we just choose, and that number happens to be less than 1. So now we're just going to pick 1 for n min. So let's see what we. Okay, so I plugged it into the calculator. So this is actually the same expression as before, except since I had a calculator, I calculated and it was 0.48, which means that my lowest order then I can use is 1, because remember you have to round to the next highest integer. And so then I'm gonna plug in 1 for this, 1 for this, and then for a max, I'm gonna plug in, what is it? 2. And then for a min, I'm gonna plug in 3. And then I'm gonna basically plug that into the calculator. I'm gonna get 1.31. This is just 1. This is 1.75. And then I'm gonna get 0.75. So I can pick any omega c here that is greater than 1.31 and 1.75. In an exam, you're either going to be told to pick like the minimum possible omega c, in which case you would choose 1.31, or you're going to be told pick the largest possible omega c, and then you're going to, in that case, you're going to pick 1.75. But we can choose any of them. So for this case, I'm just going to pick the 1.5, which is at the somewhere in the middle, basically. Most of the time, of course, when you're designing something, you're likely, if you don't know what to do, you're likely going to pick in the middle, because that way you're going to have some cushion on both sides. Okay, so once we got our omega c, we're going to basically take our base circuit, which is, if you go and look up the table of Butterworth filters, here we pick the inductor one, and if my pen decides to work. Pen's not working. What can we do? What can we do? Okay, if my pen decides to work, we're going to pick the omega c. Okay, now it's working. So we're going to have basically our circuit that looks like 1, and then you have a resistor, 1, and then this is V out, and then this is V in. And we're going to frequency scale this circuit by our capital omega c. So remember, our inductor L nu will just be 1 over 1.5, and we don't have to do anything to the resistor. So that's what we drew here. Okay, so this is a low-pass filter that meets these specs. So for our very last step, we're going to take this inductor and we're going to replace it with a capacitor, following our formula that the capacitance C nu has to be equal to 1 over omega p L. So in this case, L was 1.5 and omega p is 1400. So we're going to have 1 over 1400 times 1 over 1.5. And you can put that into the calculator, and that's going to give you the value of the capacitance that you need to put in there. Okay, so remember, this is the formula I wrote on the previous slide. So we're going to have basically C low high or L high pass filter is equal to 1 over, sorry, it's a capacitor that we want. 1 over omega p, and then the inductance 1 over 1.5, which is 1.5 over 1400. And so that gives me some number, and that's the capacitance I need. Okay, so I plug that in. Well, so 1.5 over 1400 is really 3 over 2800. And so this is my high pass filter design. So basically, when you're asked to design a high pass filter, that's all you got to do. That's it. Not much more there. And here I actually plotted the waveform. And as you can see, we indeed match the frequency response in the high end and at the low end.